Hello and welcome to another WJEC A level physics question. This time is question 17 from May 2019's Unit 1, and it's a question about using radiation from stars. First part of the question asks us to describe the main features of the spectrum of a star and state where in the star they arise. So the spectrum for a star is an absorption spectrum which has a coloured background, which arises from the surface of the star. Basically, the star is emitting all wavelengths of light, and on top of that coloured background we have black absorption lines. And these arise from the light passing through the star's atmosphere. So basically here all the different wavelengths of light are produced by the surface of the star, but certain wavelengths are absorbed by the elements that make up the atmosphere of that star. Next we're asked to use a table of some information about two stars, Sirius and Vega, to determine the ratios of the intensities of light from those stars when they finally reach the Earth. So intensity formula is power over the area over which the radiation spreads out, and that area is the surface area of a sphere, 4 pi r squared. So when we're working out the intensity of Sirius over the intensity of Vega, we've got power of Sirius over 4 pi radius of Sirius, the radius of the sphere, if you like, surrounding Sirius that the light is spread over, squared over the power of Vega over 4 pi times the radius over which Vega's radiation is spread, squared. Now you notice here that the 4 pi's can simply cancel here, so all we've got to do is calculate the power of Sirius over its distance from the Earth squared divided by the power of Vega over its distance from the Earth squared. So let's put in those figures. We got 9.7 times 10 to the 27 over 8.1 times 10 to the 16 squared, all over 1.5 times 10 to the 28 over 2.4 times 10 to the 17 squared. You didn't have to cancel. If you didn't want to, you didn't have to cancel the 4 pi's. So we plug those into a calculator and we end up with the answer of 5.68, so let's call it 5.7. Seeing as all the information in the questions to two significant figures. Next, the two stars have similar surface temperatures, and we've got the Blackbody radiation curve for Sirius, and we've got to sketch the Blackbody curve for Vega on the same axis. And on the y-axis here we have the relative spectral intensity of radiation reaching the Earth, and you can see this relative intensity for Sirius is at 5.7, which is our answer to the previous part of the question. And remember, Sirius was 5.7 times more intense, or the radiation was 5.7 times more intense when it reaches the Earth. So what we're going to do here is we're going to put our peak for the Vega graph at about 1 on the same scale. And because the temperatures are the same, and Wien's law tells us that the temperatures and the peak wavelengths are inversely proportional, we know that the peak wavelength for Vega is going to be in the same position as it is for Sirius. Otherwise, we just want to keep ourselves a curve that's underneath that for Sirius everywhere, peaks there, and sort of dies away over in that general direction somewhere. Not the neatest curve, not always easy drawing with this pen. Next we've got to determine Lambda Max, given that the surface area of Sirius is 1.8 times 10 to the 19. So first of all we're going to use Stefan's law, P equals A sigma T to the 4. And we're going to rearrange that for T so that we can find the temperature of Sirius. So T is going to be the 4th root of P over A sigma. So let's put those figures in. Power was given on the earlier part of the question, 9.7 times 10 to the 27 area in this question is 1.8 times 10 to the 19, and sigma, Stefan's constant, is 1.67 times 10 to the minus 8. So if we place those into our calculator, we end up with a temperature of 9,874. I'll just put all those figures down for the moment. Kelvin. Finally, to find lambda max, we can use Wien's displacement relationship, where lambda max is W over T. W is Wien's constant, 2.9 times 10 to the minus 3, and the temperature 9874 Kelvin that we just had. Putting those into a calculator, we end up with 2.94 times 10 to the minus 7 meters. Or if you prefer, 294 nanometers. On the final part of the question, we got an image of the Whirlpool Galaxy, one of the first galaxies photographed by astronomers. And we got different images, one using the optical or visual part of the spectrum, one in ultraviolet, one in X-rays, one in radio waves, one in infrared. And we're going to describe how these developments in observational astronomy have advanced the study of the Whirlpool Galaxy. So the basic idea is at first we only had visible light. And then by using different wavelengths, we can get more detail, or different detail. And then we just realise that there's a link between the wavelength and the temperatures of the objects here. So when we're looking at the X-ray part of the spectrum, we're seeing the higher temperatures. And that could be something like a pulsar. A pulsar is basically a fast-spinning neutron star. And neutron stars are very, very dense, very, very hot stars. Okay, thank you very much for listening. Please remember to like and subscribe, and feel free to add any comments below. Goodbye.